As Carsten said, today I'm going to focus on discussing mostly dimensionality reduction, but as you will see, you will also see quite a bit of the more traditional machine learning kind of techniques. The idea being that in order for a dimensionality reduction algorithm to to be informative, it should also be able to predict the structure property relation in your material. And you will see really how the two things go hand in hand, being able to obtain generally applicable and accurate predictions of the properties of your material is in a certain sense a guarantee that the correlations and the clusters and the families of compounds that will be highlighted by a dimensionality reduction or some sort of unsupervised learning technique is basically, we guarantee that these correlations are actually meaningful. So before I start, I want to say that, I will not get too much into the technical details because I don't think that 1 hour is enough to really get you complete from that point of view, but I will try more to present you examples from papers that and work that we have been doing, and the main people who are responsible for this work are Shondip, Felix, and Andrea, and I just wanted to make sure that their contribution is properly acknowledged. So, generally speaking, the problem that we want to solve here, if you wish, is that of representing a large amount of high-dimensional data. And these two things really go hand in hand, because if you have a large amount of data, but you know already from some magic that you have a simple way of reduce the complexity of this data to a few principal components, principal directions, then even if you have tens of millions of configurations, they really do not express that much variety, no? And you can use the knowledge of this low-dimensional representation to simplify the, just the quantitatively large amount of data points just by exploiting the fact that you have knowledge of the low dimensionality of the data itself. Sorry, I just wanted to make sure that this doesn't ring while we are talking. So, generally speaking, I have been interested in machine learning techniques, broadly speaking, for quite a few years now, but I must admit that, I have been showing this slide around for quite a bit, and my typical story here was saying that that basically, okay, we have this large amount of data that is available in materials databases, not to mention if you're doing more chemically oriented kind of research. Cheminformatics have been generating huge databases of possible chemicals for several decades now. And I've always been saying that, okay, you can try to use a computer to learn something from this data, and most of the traditional machine learning approaches sort of try to use this data to predict some properties of this data. So basically to use knowledge of the properties of a certain subset of all of the potential materials to interpolate and predict the properties, sidestepping an expensive quantum mechanical calculation. And I'm sure, having seen the list of speakers and the titles of talks, that you have seen many of these kind of applications this far. And at this point I used to say that I'm actually more interested in trying to extract some more intuitive understanding from the data, and without necessarily trying to predict the properties, but just, for instance, classifying a large amount of complicated structures into classes automatically. And what I've come to realize is that actually these two things really go hand in hand. And I will really try to show you, predictions of materials properties, but at each time try to show you how from the operation of performing this prediction, you can understand something about the material on a deeper physical level. So, in general terms, I think that in order to apply data-driven approaches to the characterization of large amounts of materials data, you have to work in a sort of a multi-scale fashion. So you have first to realize that, generally speaking, the way our brain is built to to find patterns and recognize correlations builds on identifying patterns. And if you think about it, most of the hand-waving explanation of the properties of materials always relies on saying we have a hydrogen bond, we have secondary structure in polypeptides, we have octahedra in perovskite materials whose orientation drives electronic and magnetic transitions. So really, a first ingredient in any approach that tries to understand materials from a purely data-driven approach has somehow to rely on a pattern recognition engine that can identify patterns that involve just a few atoms. So the idea here is that once you come up with a more or less abstract way of describing a chemical environment, then you can just look at a molecular dynamics simulation, for instance, and look at the probability of observing each of these patterns based on this abstract pattern description. And then this probability is basically going to tell you something about the free energetic stability of different motifs, and then you will be able to build a fingerprint that can identify these patterns in new materials with some sort of probabilistic foundation, so that can tell you, I am 90% sure that this is actually the pattern that I'm seeing. And after having started to do this, you quickly realize that one of the big challenges is actually this abstract description. So, trying to avoid putting into your initial, into your prior assumption, the way you describe environment, try to avoid to put already your preconceived idea of what should be the important motives that you are looking for. And I will spend quite some time discussing general purpose and abstract way of comparing environments and structures. And finally, when you are dealing with a material which is really complex, and for instance, pretty much anything in biology has this property, it's typically built up of many of these individual subunits. So these atomic scale patterns that you have recognized, you will have tens or hundreds of these, and they will interact with each other in a non-trivial way. And every time you have a problem like this is the kind of situations in which you need dimensionality reduction, because you will, in order to fully describe your system, you will need to specify the state of tens or hundreds of these motifs, and then the only way you can obtain a representation which you can basically put on a piece, on a set of slides and discuss in front of a coffee or a beer, is to be able to represent this complicated high-dimensional space on a piece of paper. And I will give you some examples of the kind of things that you can do with these dimensionality reduction techniques. So let me start with a very, very simple, very concrete example. How do we get around to defining what is a hydrogen bond in a purely data-driven fashion? Okay, so people have been, chemists in particular, have been debating about what is a hydrogen bond and what is a good definition of what a hydrogen bond is for decades, if not centuries. But if you think about it, ultimately, a hydrogen bond is just an arrangement of three atoms, two electronegative one and a hydrogen, and so three distances characterize completely the geometry of a hydrogen bond. And in fact, typically the heuristic definitions of hydrogen bonds that you find in the literature all rely on combinations of these distances and on basically defining a region in the space defined by these three distances or by function of them that you decide characterizes a hydrogen bond. And for instance, if you take one of the typical definitions, bond and angle definitions, and you look at the pair correlation function of water, so here I'm sitting on a water molecule and asking myself what is the probability of finding oxygen in a certain position. Basically, you see that you have very, very high peaks in the probability distribution, and the typical heuristic definitions do nothing but encircling this peak. So the question is, can we find this peak and use the exact location of this peak to define what's a hydrogen bond? And the idea here is that we first run a molecular dynamic simulation that we make a leap of faith and we assume it's an accurate representation of the behavior of the system. And then we look at all possible groups of oxygen, hydrogen, and look at what's the value of these three distances, and basically build a three-dimensional histogram. Once you do that, you can identify the maxima and just say each maximum is an important pattern. And I mean, one could go about and also discuss what the other the other maxima mean, but basically it is this lobe of the distribution which corresponds to the set of distances that people typically associate with the hydrogen bond. And basically these would be the definition that arises from this kind of procedure. And you see it follows precisely the maximum in the probability distribution. So the point is that you can do much more than this. So this, if you want, this was a relatively trivial exercise. It's not useless because, for instance, it gives you a definition that will adapt to the to the description of the hydrogen bond in your model. So if you change the functional that you're using to model water, the definition of what is a hydrogen bond will change. And that's correct, because a different functional will have a different relative free energy of different portions, and you don't have to fine-tune manually these length and angle parameters. It will tell you exactly for that functional and that set of thermodynamic conditions what is the most reasonable definition of a hydrogen bond. However, you can try to do more. And for instance, you can try to attack problems that are not so trivial. So for instance, if you look at a water wire, this is just a one-dimensional chain of water molecules that you can take as a simplified model of what's going on, for instance, in fuel cell proton exchange membranes or in the channel in a aquaporine, in some sort of membrane protein, and you add an excess proton, so you have an H plus in excess, it becomes actually very hard, even even by looking at the trajectory, to say precisely where is this excess proton, because this excess proton becomes a delocalized entity that doesn't sit at any time on a precise water molecule. So you can try to identify where the proton is, and you can do that by using the electronic structure as well. So what you can do is you run your ab initio molecular dynamics simulation, and then you compute Wannier centers. Those of you who don't know what's a Wannier center, is basically a modern version of a Lewis pair. So that's a simplified way of localizing electrons and associating a point to each pair of electrons. And then if you look at a hydrogen bond, you see that typically the two, the Wannier centers around the oxygen atom belong to two categories. You have those that sit halfway between the oxygen and the hydrogen, and these are basically the bonds, and two more that sit closer to the oxygen, and basically these represent the lone pairs. So if you look at the distribution of these Wannier centers around an oxygen atom, you find that typically on a typical neutral water molecule, you have two that are at 0.3 and two that are at 0.5. However, when you add an excess proton, a second maximum develops in the probability distribution for these distances, which corresponds to a symmetric distribution of Wannier centers. So these are Wannier centers that are nor flesh nor fish. They are not bonds and they're not lone pairs. They are a signature of the proton that is traversing your water wire. And you can partition this probability distribution and use it basically to identify the position of the proton in a probabilistic manner. And basically, this gives you automatically an index that goes between 0, neutral water, to 1, water bearing the proton, and you can see these going around. So both of these examples give you an idea of the kind of patterns that you can be looking for into a simulation of a material or a complicated biomolecule. In both cases, however, I mean, you might have recognized that I was actually putting a lot of prior knowledge and prior understanding in my definition of what a pattern might have been. I mean, the procedure with which I look for this second maximum means that I have already looked at the system for a long time, and I have picked the two order parameters that clearly, I mean, in my own understanding, must be the important ones. So at this point, I started to realize that what I needed was actually something more general and less informed by my prior knowledge about the system. And then I think it's important to have this sort of slide, which is very abstract and mathematical, but the idea is that really the object that I need is something which is capable of measuring the distance between two structures. So this is a notion which is much easier to understand and to develop than actually finding fingerprints that identify one structure, finding a finite number of collective variables that identify the state of my system. And so effectively, all that we need, as you will see, to as the basic ingredient to build a machine learning scheme to do automatically this kind of analysis is a distance that can tell me if two items in a set are similar or very different. And actually, I will use a little bit interchangeably the notion of a fingerprint, the notion of a distance, and the notion of a kernel. And at this point, you have heard probably already the word kernel several times during these 2 weeks, but from all practical purposes, all that I care about is the notion that a kernel is a function that, it tends to a finite value when the two structures are very similar, and it tends to 0 when the two structures are very different. And, a typical, you always have a mapping between a positive definite kernel and a distance, and vice versa. And actually, if you can define a distance or a kernel, it's also very easy to define data-driven fingerprints. And this is not something that I'm going to discuss very much in detail, but it's basically the mathematical foundation of all of these machine learning schemes that are based on kernels. So how do you define a kernel function that can compare two structures? And here my objective is really to make this construction as general as possible. So I don't want to be using, a graph representation of the bonds within my structure, because perhaps my structure will be an ionic crystal for which I cannot define clearly bonds meant as covalent bonds. So I really want a completely general scheme, and I think that one of the most effective ways to build something which is general purpose is actually to change the focus, and rather than looking at a way to compare structure, focus on a way to compare atomic environments. In a certain sense, this is something that really builds onto the intuition of electronic structure theory, that you can, that electronic matter is nearsighted, so that you can, when you have a large system, you can break it down in local pieces, and each piece makes sense in its own, and the properties of the different pieces can then be pasted together. And so basically what I will show you is how you can start by a kernel that only tells you whether two groups of atoms are similar or different to each other, and combine these into a kernel that you can use to match entire structures or entire molecules. So how can you do this? You have had a presentation by Gabor earlier that went into very much detail about the definition of this smooth overlap of atomic positions. Just as a reminder, the basic idea is that you sit on the two atoms that you want to compare, I mean, whose environments you want to compare. You deploy Gaussian hills on each of the atoms around your center. Then you overlap the centers, and you compute the the overlap integral between the two Gaussian densities. Actually, as you will see later on, I really think that one should think of these densities more as probability amplitudes, because then this overlap integral becomes something which is really equivalent to a scalar product between two wave functions. So I think that this sort of reveals some analogy between this way of comparing two environments and some sort of quantum mechanical description of the system. Then, I mean, if you remember Gabor's presentation, you have to do a number of different operations to make sure that actually this overlap integral satisfies the fundamental symmetries of the problem, but I will not get into detail. To me, this is just a very smart way of comparing two groups of atoms. And the real question is, once you have done this operation, how can you build something that you can use to compare entire structures? So a simple thing that you can do is say, okay, I mean, I can do this for each pair of environments. So I can sit on each of the atoms in structure A and in structure B and compute this similarity kernel between this environment and this environment, this environment and this environment, and so on and so forth. And then I can build the compound, the global kernel, by combining together in some way these individual kernels. And you can do this in different ways. So a way that would seem very intuitively a good one is basically to try to find to match one-to-one the environments in the two structures and find the combination that maximizes this kernel. Another possible way, which is simple-minded but actually works beautifully, and I explain you why, is you just say, I put everything together, without caring whether the match is good or bad. I just average over all of the possible pairings. And something that actually we find works particularly well, as it is often the case, is basically a technique that allows you to interpolate between these two extremes. So it looks mathematically complicated, but it's actually cheaper to do than this matching. And the idea is that basically you do something which is some sort of maximization, which is, however, regularized with the information entropy of this matching matrix. And depending if you set this to 0, you recover this limit. If you set this parameter to infinity, you recover the unbiased average limit. Okay, so, I mean, what does it mean to pick one choice over another? So, I mean, what does it mean actually physically to do something like this? I mean, this seems like an operation which is very unnatural. I mean, I'm putting together information on, I don't know, perhaps the similarity between a carbon atom which is sp1 hybridized and one which is sp4. Does it really make sense? Well, actually, you can show that formally, if you build, and this you have seen, this is basically an expression for a kernel ridge regression machine learning of the energy. So if I write the energy or a certain property of a molecule A as a weighted sum of kernels between my structure and a number of reference structures, and I build this kernel as just a unweighted, just a plain average of all the possible kernels, you can show that this is equivalent to assuming that your energy function can be broken down in, atom-centered energies. So there is basically a correspondence between taking the simplest possible form of combination in building your global kernel and, in a certain sense, the simplest possible expression for energy of an extended system, which is breaking it down in atom-centered contributions. Okay? So this is actually, I mean, this can be a complicated many-body kind of expansion, because, I mean, this is just saying that the energy on a certain atom will be an arbitrarily complicated function of the positions of all the atoms around it. However, you are making this assumption of basically additivity, which is something that helps tremendously in learning any property for which you can assume that it will be additive. So something like this, for instance, will fail catastrophically if you try to learn a band gap, but it will work extremely well if you try to learn the total energy, because the total energy is something that can sort of be decomposed in subsystems. Something like the band gap is something instead that requires knowledge of the entire Hamiltonian. And actually, I will show you one example, not concerning band gaps, that using this sort of entropy regularization that goes beyond additive combination of the kernels is one way to learn properties that don't decompose naturally into atom-centered contributions. So now I just want to give you a few examples of how you can use these to machine learn properties. And the reason why I want to show this is that for each example, I will also be able to show you how, from the successes and the failures of the learning operation, you can learn something about the physics that underlies your system. So for instance, let's take what is one of the national sports in the machine learning community, which is learning the energies of the GDB9 database, which is an extremely useful test, benchmark database that has been put together by several people, many of which are or have been in Berlin, and basically, so. One aspect that we tried to do when doing this exercise was actually to make sure that we were making something useful. In this sense, so this database in itself contains a bunch of DFT-optimized geometries and the associated ground state energies. And the typical benchmark exercise, and I will show some of these benchmarks later on, is to learn the DFT energy taking as an input the DFT-optimized geometry. Now, this is clearly a pointless exercise, because in order to get the DFT-optimized geometry, I needed to run a DFT calculation. So actually, we also did two other things, which were basically, starting from knowledge of the DFT geometry, predict the couple cluster energy, and much more challenging, starting from knowledge of the geometry optimized at a semi-empirical level, predict directly the couple cluster energy for the DFT geometry. So basically, we never, these guys have done the DFT optimizations, so we have the reference values, but in the test exercise, I pretend that I don't know the DFT geometries, and I directly predict the optimized energy starting from a non-optimized geometry. So what you can see, so you have probably seen many of these again. This is a learning curve, which basically shows you how the error in the prediction decreases as I add more and more molecules to the training set for my problem. And basically, you can see how, you can predict directly the couple cluster energies, getting to an error below a kilocalorie per mole. But actually, if you exploit the fact that you know already the DFT energies, and this is something which is well known, you can actually bring down the error to virtually zero. And what is interesting is that, well, first of all, you can get pretty good predictions even just using the semi-empirical geometries. But what is interesting is how actually you get down. So here what I'm doing is I basically use as input 20,000 structures okay, for which I have done both PM7 geometry optimizations and the DFT optimizations. And I learn from all of them, trying to understand how I can predict the coupled cluster energy. What I've done in this curve has been using for only these 20,000 train structures information on how much the PM7 optimization went wrong. So basically, I am discarding the structures for which the PM7 geometry was very different from the DFT geometry. When I'm testing, I don't use this information. So there will be some of the structures in the test set for which PM7 would fail badly, and I don't know. I'm not using this information. But just the fact of discarding the structures for which I know that something is going wrong improves dramatically the accuracy of my predictions. And this, in my opinion, is important because it gives you an example of how sensitive machine learning is to problems in your training set. So as soon as you have some inconsistencies, as soon as you have some structures computed at a different level of theory or with a different number of k-points, or you have some structures for which the underlying assumptions of the approximate method fail, your machine learning is going to take a very, very hard hit. And to me, this is one of I will return to this later. Consistency check on databases that go into machine learning models is extremely important because machine learning models are extremely sensitive to inconsistencies. And then, I mean, I just want to show you a little bit what's the, the limit of accuracy that you can reach with this kind of techniques. So, for instance, using this scheme and using, here we stopped at 20,000 structures because, I mean, computing coupled cluster energies is expensive even for small molecules. But if you restrict yourself to the academic exercise of learning DFT starting from DFT, we can push it up to 100,000 and we bring the error down to basically a kilojoule per mole. And actually, on a smaller data set, you can try to play different games and try to learn something about chemistry by checking how different benchmarks work. So if you just apply this same scheme that I discussed this far to this smaller data set that only contains 7,000 structures, we get down to a number like this. So it's half a kilocalorie per mole error, which is, I mean, it's less than, it's basically 50% less than what was the state of the art, but you can do much better than this. And how can you do better? Well, you can learn a lot from how you can do better. So in the construction of these of the overlap integrals that enter these SOAP kernels, you normally assume that that you only overlap oxygen with oxygen, sulfur with sulfur, carbon with carbon, and hydrogen with hydrogen. However, you can generalize the framework and basically you say, okay, to each of these probability amplitudes that correspond to oxygen, carbon, hydrogen, and so on, I also associate a little bit like a spinor, no? I associate an abstract ket that describes the chemical nature of the different elements. And then when you formally take this overlap, you don't need to make this overlap between these spinor-like components orthogonal. You can take any form you like, and here, for instance, we tried something very naive, which is just taking this sort of alchemical overlap object to be the difference in electronic, Gaussian function of the difference in electronegativity. And, just doing this brings down the error by 20%, which at this level is not little accomplishment. What do we learn from this? Well, we learn what chemists have known since before Pauling, which is the fact that different elements behave in similar ways. And if you include this information, in the making of your machine learning algorithm, you can gain a substantial amount of accuracy. And of course, there is a lot of potential, and we are playing around with different ways of optimizing these matrix elements, not only because we can make the algorithm more accurate, but also because the optimal elements can also give us some sort of purely data-driven redefinition of electronegativity in a certain sense. Another very important aspect that we keep hearing about, but I had never seen in such a clear way, is the scale of chemical interaction. So what's the length scale at which, what is the energy scale associated with interactions at a certain length scale? So what you can try to do, for instance, is to, since we have a definition that is based on local environments, we can cut off these local environments at different levels. And what happens, in my opinion, is very, very instructive. So if you use an extremely short cutoff, 2 angstrom, so in the definition of the environment, we use a length scale of only 2 angstrom. What happens is that initially this kernel, when you have just a few training structures, works extremely well. Why? It works extremely well because there is a small amount of information in a sphere of 2 angstrom, and so with just a few structures, you can cover a lot of the potential configurations. However, as you keep pushing to larger number of training structures and lower error, at a certain point, you sort of saturate. Why are you saturating? You're saturating because the information on the residual is encoded in longer range interactions. And indeed, a kernel with a longer cutoff does better when you increase the number of training structures. And we did this also on the larger GDB9 dataset, and there you see that when you really push to larger and larger number of training structures, the even longer length scales become important when you want to push the accuracy below, let's say, the half kilocalorie per mole. And so, here we learn something about the scale of chemical interactions, and you can use this information to actually make the learning more efficient, and you can build a kernel which is a combination of multiple kernels. And this basically gives you consistently better accuracy across the board, and we basically can push the error down to 1/4 of a kilocalorie per mole. So another example, you can also use these, and this is data from Karsten actually, so you can use this scheme to machine learn the energy differences between different levels of electronic structure theory. Now, I could, quote again the fantastic accuracy we get. Basically, we can start from GGA and predict couple cluster level accuracy with just 20 training structures. Here it's a very simple problem. We just have different conformers of glucose. Still, with just 20 reference structures, we can basically get couple cluster level accuracy with only 20 references and just running DFT. So, however, I want to point you at the insight that you gain by this exercise. So this is a figure that contains a lot of information, so bear with me. On the upper triangular side, I'm showing you the intrinsic discrepancy between 2 techniques. So you see that basically semi-empiricals have a very large error compared to anything which contains exact exchange or post-Hartree-Fock terms. And you see that there is a very considerable improvement when you go from plain GGAs to hybrid functionals. However, if you look at the lower triangle, which is showing you the error after you apply the machine learning correction, you see that basically there isn't much difference between GGA and hybrids. So what this is telling us effectively is that the correction that comes from from exact exchange is very easy to machine learn. And typically this means that it's a short range correction. And you can also learn even more by basically decomposing the error into atom-centered contributions. So here, these are basically, this is the glucose molecule, and this is the lowest energy and the highest energy structure in the data set. And what I'm showing is basically I'm computing the contribution of each atom to the energy difference between PB and PM7, for instance. So you see that when you look at a semi-empirical method, you know, the error might be not so large, but actually it comes from a cancellation of errors. So you have some atoms that are very much too stable and some atoms that are too unstable, and this just balances out. But this is an indication of the fact that these semi-empirical methods are indeed semi-empirical. You know, you try to get the right answer, but you don't necessarily get it for the right reasons. If you look at something like the difference between hybrid and the GGA, you see that the discrepancies are much more regular, and you see that there is a large error in particular associated with the closing of the ring in the glucose molecule. So basically what you understand from here is that exact exchange is very important to describe the energetic of this ring opening process. And basically, if you look, it's much harder to find clear-cut signals when you look at the couple cluster, the difference between a hybrid and a correlated method, basically because these are complicated correlations that you cannot represent so easily in terms of atom-centered contributions. Okay, now this sort of closes the supervised machine learning section. I wanted to get now, finally, to the dimensionality reduction aspect. So all of these kernels that I've shown you can be used to machine learn can also be used to define a distance. And in general, I think that really distances are the most natural building blocks to do these dimensionality reduction techniques. And I want, again, to start from a concrete example, classifying the structures of an oligopeptide, or I mean, probably this community would call this a polypeptide. I mean, the people working with proteins, up to 20 is probably an oligopeptide. But anyway, so you can take this molecule, you run accelerated molecular dynamics run using an empirical force field. We really don't care about accuracy at this level. And what you observe is that this molecule can exist in a number of different forms, and these different forms, biochemists have learned to classify in terms of alpha helix, beta sheet, random coil, so in terms of these local patterns. So for the moment, we're working on sort of rediscovering these with data-driven techniques, but here I want to focus more on how you can classify the overall set of angles that describe the state of the molecule. So first of all, it would be a little bit suicidal to use as the input to represent the state of this chain the coordinates of all the atoms, right? Why? Well, because this is a polyalanine, and basically the backbone is relatively rigid, and you really don't care about the orientation of the methyl groups. So something which is reasonable, and that I strongly advise you to do, is to reduce the dimensionality of your problem to the maximum level you can using some obvious considerations. So for a system like this, it's really clear that just the backbone dihedral angles are sufficient to fully characterize the state of the backbone. There are algorithms that, given the sequence of backbone angles, build you the extended structure of the protein. So really, all the information is encoded in those 24 numbers. Now, the problem is that each structure, even if represented at this simplified level, consists of 24 angles. So it's basically described by a vector of 24 numbers Furthermore, living in a horribly complicated non-Euclidean space, because these are angles, so the geometry of the space is basically a hypertorus. So how can we understand something that lives in a 24-dimensional hypertoroidal space? That's the question. So the idea here is that each structure is a point in this space, and what you can do is measure the distance between these points. And this could be the Euclidean distance, as simple as that. And then, in order to find a simple low-dimensional representation, what you can try to do is basically, set different reference points on a plane and just jiggle them around until all of the relative distances match the distances that you had computed in the high-dimensional space. If you succeed, this low-dimensional representation is going to be a faithful representation of the relative position of all of these reference structures. And once you have done this, effectively, it's like you have, a set of reference points in the, in the mind-boggling 24-dimensional space, and a set of reference points in 2D that correspond to them, and you can use these to build a continuous mapping between the high and the low-dimensional space. Of course, this operation of matching distances would only work literally if the high-dimensional points happen to lie on a hyperplane, which is, of course, a very strong assumption, particularly if your space is highly non-Euclidean. So, the technique that we chose to use to solve this problem, which we call sketch map, basically starts from something which is called multidimensional scaling, which basically tries literally to do what I just described. So you define an objective function that tells you how much the distances mismatch between the high and the low dimensional space, and you jiggle around this point until you achieve the best possible match. And what we did in order to make the technique suitable for atomistic data was basically to say, okay, the problem is that these distances at small distances will correspond to stuff we don't care about, thermal fluctuations, small molecular rearrangements. And if two things are completely unrelated to each other, we don't care about representing accurately their distance. So what we do is we transform the distances so that we focus on the intermediate range that give us information on structures that are kinetically related to each other. And actually, if you apply these to what we originally envisioned this for, which was biochemical simulations, you find that, so if you describe the folding landscape of this oligopeptide using conventional order parameters, you find that the alpha helix is very stable, and then it looks like there is a, the unfolded ensemble, so a bunch of structures that are all unstable. But actually, if you run a simulation and you start from a random coil, it often gets stuck into structures that look stable and they stay stable for hundreds of nanoseconds. So what's going on? Well, what's going on is that it's not that these structures are not stable, it's that these coordinates do not have enough resolution to distinguish this structure from that structure. And if instead you use a data-driven technique to define the collective variables, now each of these structures is correctly identified as a local free energy minimum. Now, how can you use these to attack big data? And I would put big in inverted commas because we are speaking here of a few thousand structures. How can you use these to tackle big data databases? So this is, for instance, again, data from Karsten. It's a database of peptides and dipeptides in the gas phase. And for each structure, we have like between 100 and a couple of thousand conformers that sample all the possible local minima in the potential energy surface. So what you can do is you define distances between structures using this SOAP-based kernel, And then you can, for instance, cluster these structures with a hierarchical clustering scheme. And you immediately find that actually, yes, you might have 1,000 structures, but actually they all partition quite naturally into a few groups that differ, for instance, for whether they are folded or extended, what kind of hydrogen bonds are present or not. And you find this, this set of structures which is very separated from all the others. And then when you go and look at them, you probably don't see it here, but basically, in this case, there has been a proton transfer going on, which is something that happened because Karsten and his collaborator, Matt in particular, ran these searches using DFT. So one of the downsides of using DFT is that unexpected things can happen, and you need these kind of techniques to recognize that something unexpected has happened. Otherwise, you might just go about and ignore the fact that your search has found something interesting. And then, you can see that this clustering actually corresponds very well to different structural parameters. And in particular, you find that the backbone dihedrals are not the best variables to describe this data set. Again, because having done the search with DFT and having included fairly high energy structures, also the isomerization of the peptide bond is observed. This happens very rarely in a biological context. Most peptide bonds are trans in biological contexts. But if you do your search including high energy structures, also cis configurations can be found. You can also analyze this data set using SketchMap, and this is basically an alternative representation that rather than using this hierarchical clustering, just does a two-dimensional map of the molecules. And you see now you can identify very clearly these structures that have undergone a chemical transformation, and you can see that all of the stable structures are lying in this half of the plane. And these are structures in which the side chain, which is positively charged, folds and gets close to the oxygen atoms. Now, if you add cations to this molecule, you can see how the stability changes. And for instance, if you add a cation, now the stable structures are almost all those with the open side chain, because the cation is complexed by the carbonyl oxygens, and then the other positive entity is pushed away. So, for instance, if instead you look at the neutral amino acid, there isn't such a clear-cut distinction between stable and unstable structures. And if you look at the uncapped peptide, you see that the addition of the cation changes completely the conformational state of your molecule. So you can really use this representation to understand something and convey a message in a very clear manner. And something which is important, in my opinion, is that you can also use this kind of analysis to identify inconsistencies in the data set. So here, in particular, what we're doing is looking at so for each of the clusters that we find, we have a measure of how structurally diverse they are and how energetically diverse they are. Now, you don't expect this correlation to be perfect, because you can have structures that are very different but very similar in energy, but normally you would expect to find something that shows some degree of correlation. For some of the structures in the database, you were observing a correlation plot that was looking like this. So this is basically telling you that you have clusters that are extremely similar, extremely homogeneous from the structural point of view, but have massively different energetics. And actually, this triggered us and Karsten to look back into the data and find that some of the structures had been computed at different levels of theory. And these kind of discrepancies would make machine learning completely pointless, because your database would contain contradictory data. Effectively the same structure would be tagged as having two very different energies. So this kind of automated analysis, I believe, will be extremely important as databases of structures, perhaps of heterogeneous provenance, are combined together, it's extremely important to make sure that they are consistent. So as a final example that I want to show you, this is still work in progress, but basically we're trying to apply this technique that we have sort of, this far I really have only shown you applications to gas phase molecules, so we're starting to go to molecules and to materials in the condensed phase, and in particular we're looking at molecular materials. So here we have a few hundred actually polymorphs from the group of Gramidae for substituted pentasines molecules, and we have in particular pentacene and 2 different azapentacene molecules. Now this is meant to form very regular structures. You see it as a regular nitrogen substitution pattern, and this instead is meant to be giving rise to very disordered structures because it cannot form a regular stacking of the planes. So what you can see is that basically machine learning works beautifully. In all cases, we can easily get errors below a kilocalorie per mole. So this is really useful also if you want to do crystal structure prediction. You can use this kind of techniques to predict energies at the DFT level without having to run a DFT calculation. But what is also very interesting, again, is the kind of insight that you can extract. So, for instance, the PhD student, Jackie, in the group of Gramidae, had painfully looked at all of the 200 structures and classified them manually in different heuristic classes. You know, these molecular crystals can stack in different ways. Basically, just by automatically analyzing the database, we can find clusters that in some case correspond to the heuristic classification, and in some case disclose very clear patterns that are not captured by the traditional techniques. And this also works very well for the regularly substituted pentacene. Again, you know, there is a heuristic classification, but the automatic classification recognizes that there are more precise patterns. And instead, for the irregularly substituted pentacene, you see that this classification thing doesn't work. And this is just because this is a very glassy landscape that escapes this definition. So I just want to show you that sort of a live demo. So we are in the process of basically working out a web interface in which you can upload your structures, build a sketch map of them. So for instance, this is a database of about 1,000 polymorph of ice. And basically, you click on a structure, it gets loaded up here, and you have a list of the properties of all the structures. We have something similar for organic, inorganic perovskites. You just load up all of your structures, and then you can recognize that you have different motifs. So actually, these are the proper perovskite structure. You see the octahedra and all of that. But if you do an extensive search, you can also find structures with very different connectivity between the, this is the what they call the delta phase, which is actually bad for photovoltaic properties, and so on and so forth. And basically, the objective is to make sure that you can upload your structures and get these automatically. So with this, I will wrap up because Carsten is standing up threateningly, and thank you for your attention.